Good morning, America. Now, go ahead, skip to the timestamp if you would like to go ahead and see the code in action, along with visiting down in the description of the video for the GitHub link for the code. Keep in mind that it was made by a recent high school graduate, aka me. Yay! Recent college acceptees, let's go. So keep that in mind because there are lots of optimizations in the code. Now, this part of the video segment with my beautiful face in it, is going to go ahead and talk about the generalities of why and why not to use the program code or the system setup in general. And from that, maybe you could learn something, maybe you won't learn something. The main point is that you're gonna watch a recent high school graduate, a recent college acceptee, whatever, talk about machine stuff. So be prepared to correct me, and if you do correct me, please comment or email me. More than likely email, because that's probably the only way I'll respond. Now, with that out the way, let's begin on the Y's. Oh boy. Now the letter Y in the alphabet is oftentimes almost dead last, and nobody really considers it. But in engineering, we do consider it. So, the Y of this plane is actually excuse me, I got the hiccups. But the Y of this project is essentially a cheap Arduino based system, so not everyone has a lot of money to spend on anti-collision devices. So if you're going for a cheaper plain alternative, but you still want to be an autonomous RC control, and you want to, make sure that your plane, if it was to see a random building, see that you didn't account for it or something, then you could have a safety feature such that, oh hey plane, if you see some building in front of you, then just simply yaw away from it. Bingo, genius, right? Oh boy, wow, that's so innovative. Wow, a $20 Arduino system to avoid buildings and people. I wonder what could go wrong. And unfortunately, a lot does go wrong with that system. So let's discuss on the why nots. The why nots are primarily as follows. First of all, this code, at least the hardware that I used, it only has a range of 4 meters. So that's a big oopsies in terms of safety, because what if your plane can't turn that fast? Like, what if your plane had a speed of, I don't know, 35 to 40 miles per hour, and through that it comes towards a wall, it has 4 meters to turn. The question is, could your plane turn that fast if it was to come in contact with an imaginary invisible wall? And the answer is, entirely depends on how you built your plane and how you want to modify the code. I left the code pretty open-ended, but that doesn't mean it's perfect for everyone. So be sure that when you implement the anti-collision device, that you know for a fact that, hey, my plane, based off some testing I did, could turn in 4 meters. Preferably 3, so that gives you a 1 meter kind of safety buffer. But I digress. It's your plane, it's your lawsuit. You do you. And before we start into our machine discussion, let's discuss how things generally work before we look into the code. So here we could see that the ultrasound sensor is picking up the movement of the plastic bag over the vent in the top kind of area near the windowsill. And when it picks up this plastic filament that's moving back and forth, aka the plastic bag, it's essentially reading 2 distances. One distance is the distance from the ultrasonic sensor to the background, which is, say, hypothetically, just 3.5 or so meters, for example. and when the plastic bag, the filament, moves in front of that windowsill, it's going to read 3.4, for example, centimeters. So it's that kind of difference in the two distances that is causing the servo to rotate and the red LED to blink, because inside of the program, the ultrasonic sensor, the input, is telling both of these objects that, hey, there is an object that's potentially moving or getting closer to us. Let's start putting an input signal. And that's why you see all of this. Now, as for how each of these are going to get controlled, please see the GitHub link description as it discusses the conversion rates between these two. But essentially, the servo is taking the input data from the distance to rotate it accordingly in degrees. And the red LED is going to be dependent on the velocity, or how quick that object is moving back and forth and coming towards you, in order to blink faster. So essentially, the faster this red LED blinks, the faster that plastic filament is moving, and the faster that plastic filament is moving, then well, if it was moving towards you, then the servo arm would rotate even further. Inside of the code, I also left a commented description so that you could uncomment it and provide your own method of rates of change for this servo. Alright, now let's move on to the live video demonstration. I'd like to apologize ahead of time for my vertical recording, as that is a sin beyond any type of engineering practice, or malpractice in this case. However, I think that it still provides a rather excited view of things. Now let's go test it, boys. So here I have a flat box behind me, so constant little integer value of 45 centimeters, pretty solid, pretty cool stuff is what this thingy is reading. So right now it's at 45 degrees, but as I put my hand closer, the degrees will decrease and decrease until it's just about 0. So I'm getting my thing closer and closer and closer. How cool is that, guys? Yo. Now obviously the degrees change ain't too different. It's about just a few dozen degrees, so it doesn't really make sense for it to be some dramatic super duper shift, but I just thought it was cool and I thought I'd share. Alright, see y'all. Guys, I made a motion detecting sensor. So basically how it works is this thingy in centimeters equals this thingy in degrees. So like you have 15 centimeters, 15 degrees. You're gonna look at that sensor over there without the hand magic in the way. So here we go, lads. Taking my hands inwards, so the degrees is gonna shift down. Taking it back out. I'm gonna do it faster now. Good bit faster. And I'm just gonna go crazy. Wee, it's going places. Zoom. Oh, and there's gonna be a slight lag because this is measuring at 20 times per second, and it's kind of hard to adjust the sensor to that. So probably gonna have to delay it to about 10 times per second. I don't know. I'll figure it out. Alright. Just wanted to show you guys the cool motion stuff before I take it down and replace it with actual useful modifications.